Good afternoon, and thank you all for coming. Apologies for scheduling this seminar in the fall break. I didn't even realize that it was a fall break. But it shows that all of you are very motivated to come during the fall break, walk all the way to a corner of the campus, and I'm really, very grateful for you. And it is really a treat for you today. We have very distinguished and accomplished researcher, Professor Bonnecaze from UT Austin. I should tell you a story to put this in context. There was a workshop organized by DOD last September on this NNM thing. So I was there, and one of the program officers made observation. There was a discussion about nanomaterials, and this guy is obviously about manufacturing. He's coming from the DOD manufacturing office. He made the comment that I'm tired of researchers coming to me with micrograms of wonderful material, nanomaterials. I would like to know how to manufacture them in tons. And Roger has a solution for early beginning of solutions for such systems. How do you produce these highly functional, highly structured nanomaterials in large quantities so that we can reap the benefit of these wonderful materials. And there are, of course, historically in chemical engineering, a number of examples where chemical engineers have come in and enabled large-scale manufacturing of lab-scale discoveries. Penicillin is a good example of that, and I think photovoltaics is also a good example of that. So today we are going to be introduced to unit operations in manufacturing. Roger did his bachelor's from Cornell and a PhD from Caltech in chemical engineering. And I think spent a year in Cambridge as a postdoc at the Department of Applied Mathematics and Theoretical Physics, the mecca of that area for anybody in the field that you know. And he has been at UT Austin since 1993, and he has received a number of awards. I mean, we end up giving the whole seminar if I have to do that. But he has won the NSF Young Investigators Award, AACT Thomas Barron Award, and he's actually a fluid analysis, and he's a radiologist from the background. I guess he's a fellow of the American Physical Society, AACHE, AAAS, etc. So it's a long list of accomplishments. It's really a great pleasure to welcome you. I'm grateful for taking all the way to those flight delays. So please join me in welcoming
Well, thanks, Kumar, for that very warm, wonderful introduction. And thanks for inviting me, and thanks for all of you coming here on your break. I appreciate that. And so what I want to do today is tell you a little bit about our work at Nascent. So the Nascent name is derived from our center, which is funded by the NSF, on manufacturing systems for mobile computing and energy technologies. So what I'll do is just give you a very brief introduction to Nascent and what it's like, and then talk about this unit operations concept for nanomanufacturing. So for chemical engineers in the audience, this will probably, what I hope, will be a lot of nodding of heads and a lot of course, why shouldn't we be doing it that way? But if you're in other fields like mechanical or electrical engineering, it's actually a more surprising or interesting way of thinking about it. And then what I'll do is I'll talk about models and simulations for just two nanomanufacturing processes that we're working on. One of them is on UV nano imprint lithography. So we're working on both wafer scale and roll-to-roll processes. Today, because of time, I'll just focus on the wafer scale, but many of the ideas that I'll present are transferable to roll-to-roll. And I'll talk about some work on modeling directed self-assembly of nanoparticles that we're using right now to help guide experiments that we're doing, and then I'll end with some concluding remarks. I'd encourage you to feel free to interrupt me with questions as I go along. Thanks for more interactive and interesting thoughts, so feel free to pipe up and make a question. So, Nascent is one of 20 NSF-funded engineering research centers. So we just started our 4th year. Roughly speaking, the center has a budget of about $5 million, so about $1 million $4 million comes from NSF, and the other $1 million comes from industrial sponsors and other sponsored research projects. We have about 75 grad students and postdocs and faculty members as part of the team that come from chemical engineering, mechanical, chemistry, material science. So it really is a multidisciplinary work environment, and what maybe makes this graduate student experience different from other ones is that the grad students really are working with graduate students from other disciplines, so they get a different perspective on how things are done. The NSF ERC program is kind of unique in the sense that it does have this interdisciplinary component and has this very strong interaction between academia, industry, and government. So some of our partners are the University of New Mexico in Berkeley on the academic side. We have these large companies involved in the center. So we have companies that basically make, nano manufacturing tools like Tokyo Electron and Canon and Applied Materials and Lam. We have companies that use them or develop materials like 3M, Nandakumar Print, and ultimately companies that want to make nano-enabled devices, say for military applications like Lockheed and Raytheon. We have startup companies, smaller startup companies as well, and as well as national labs. So the vision of NASEN, right, is to create scalable and cost-effective nano-manufacturing infrastructure to basically, as Kumar said, take that square, or milligram of a nano material or a square millimeter of some interesting nanostructure and make it into the volume or production level required to have an impact on society. Okay? And so we kind of view this as, if you think about resources versus level of development, there, of course, as professors, we never think there's enough money, but there's a lot of money available for seeding new ideas. Okay? And these oftentimes result in lots of interesting things in terms of different ways of patterning or assembling materials, different 1D, 2D materials, new metrology techniques, etc. And ultimately, you want to use these to make some devices that society wants, like more energy efficient phones and iPads, maybe wearable electronic devices and solar cells, better batteries and supercapacitors, neuromorphic electronics to basically connect our brains directly to electronic devices or mechanical devices. And then, once you actually have defined and established a viable product, there's also a fair amount of resources available to deliver this. There's this dead zone in between, which is how do you actually go from these ideas here, right? These are the things that make the cover of Science and Nature, and you hear on NPR on the drive to work, that's going to revolutionize this. It's a lot of work to actually go from the revolution out over here. And so we view ourselves as trying to bridge that gap. And so what we're trying to do is provide the systems, the processes, what chemistries are required, what conditions are required, the metrology, how do you measure things at the nanometer scale while you're producing it at the meters per minute scale, and then multi-scale models of what's going on in these processes. A lot of our prototype devices, say for roll-to-roll nano imprint, we're printing 80 millimeter wide sheets, okay? But if you want to make a display, say for that television screen in the back there, it needs to be 300, 450 millimeters wide. Now we're not going to build a prototype that large because it's expensive and the materials are costly, but we want to be able to scale up. And so we basically develop models that are validated against our devices in the lab. Now we can use those with confidence to scale up to whatever industrial scale is required. So this is where we're aiming for. So let me give you a couple of concrete examples so you have an idea of what kind of useful nano-enabled devices would we want. So one is basically your polarizers in your tablet or iPhone. Okay? So these basically polarize the light that comes to your screen, and you basically burn a lot of the power from your phone backlighting this image. Okay? And right now we use basically organic polarizing films. Right? What has been shown, theoretically and also in small samples, is that if you, instead of using these organic films, you make a grid of essentially 50 nanometer aluminum lines. These are 50 nanometers wide, and they're spacing, from top to top. The gap here is 50 nanometers. These are called wire grid polarizers. And these have better contrast ratios. They're thinner. They're, if you can make them cheaper, you can reduce the bill of materials. But most importantly, they give you a longer battery life. This is sort of the big selling point. So if you can make these kind of structures at size scales that go from your phone to, say, a large television display, you can really revolutionize in terms of energy consumption and image quality for displays, right? So this is an example of a nano-enabled device, right? There might be a lot of other components here that aren't nano, but by putting this one piece, you can improve efficiency greatly. Another example is bit pattern media for magnetics. And so the idea here is, instead of having sort of this continuous magnetic domain that you write some areas and don't write other areas, you actually have isolated magnetic zones which you can either flip, magnetize in one direction or another and become your bits that are 1 or 0s. And what's been shown is that by isolating them, you can basically make these regions smaller per bit than you would have in this classic way. So this is so-called bit pattern media. The idea here is you want to be able to get to very high densities, like a terabit per square inch hard disk memory. And so the way to achieve this is basically, one way that's being pushed is using imprint lithography. However, to make the templates for imprint lithography, which I'll talk about in a minute, you probably need to use directed self-assembly of blockable polymers, or you might use directed self-assembly of particles that I'll talk about. But if you can do this and make this nano-enabled device, you can significantly increase the memory density that you have in various devices. And even though you might think that we're going to solid-state memory, say on your laptop and your phones, all those giant server farms that we're accessing all the time when we use searches, they're still basically running off these disks because that's the cheapest and easiest way to basically create these memory storage devices. Okay, so in order to basically create, a nano-manufactured product, right? What you really need are two pieces. One is a pilot facilities for process development and device prototyping. Okay, what I've found in my career consulting with a lot of companies that do nano-enabled devices is that they have two challenges. One is they have to make a product that somebody actually wants to buy and is viable. Okay, and they have to figure out how they're going to make it, because they're doing things that people really haven't done before. So they usually have twice as many problems as, say, somebody who's trying to come up with a new frying pan or something like that. Okay, and so there's really a need to have sort of a facility or a foundry, if you like, that generates sort of preliminary data, understand how to prototype a device quickly and what process you need to develop it. And then what would be great in order to do that is if you had a well-understood set of standard processes that you can mix and match and add in order to make your desirable, make your product. Okay, and this is really important because sometimes you're making relatively small lot production. You want to be able to mitigate risk, and you also want to explore process flows, through simulation, which really can only happen if you have sort of a set of standardized processes. So here I show actually a print of some of these wire grid polarizer regions. Okay, so this just gives you a sense of the scale of it and the continuum. Some of the other things that we can do at Mason is we can actually take silicon, do full CMOS on it, and then shave off the top 30 microns and actually make a flexible silicon, which the idea here is you don't want to bend it or anything like that, but you want to be able to maybe wrap it around, say, a cockpit of an airplane or somewhere nearby. Or you want to basically mount some photonic device and some kind of glasses for augmented or virtual reality. So this is where the unit operations concept comes in. So as chemical engineers, we're all familiar with this idea that whether you're building a giant petrochemical facility or a smaller pharmaceutical facility, it's all basically pumps, pipes, reactors, and separators, and we have a really pretty good understanding of how these work, right? And the advantage of this is that since we understand how these work, it used to be 30, 40 years ago, we had these rules of thumb and sort of correlations to design them. Now, pick your favorite simulator, Aspen, whatever. You can do a pretty good job designing the entire plant in silico and explore things, right? Nobody designs an airplane without doing a full-blown simulation now. Same thing with a car. Okay? Amazingly, in the microelectronics or nanofabrication business, it's done pretty much empirically. Okay? There's still a lot of this drive to basically you take a tool you have and you make some changes here and there, but you don't really necessarily design the whole plant from top to bottom, doing a full-blown simulation. So, just to give you a concrete example of a unit operations process flow, I'll talk about like wire grid polarizers. So you might have your original film, the original substrate, say some polymer that has a protective film. You basically do a metal deposition. You then do a slot die coating to put on a adhesion layer. You then do the nano imprint, where you basically put in the structures, say for making the lines or whatever structure you want. You then do a metrology, say with some scatterometry to figure out, did I actually make what I thought? You can do an etch to remove the metal in certain locations. You can recode it, go back and make sure that you made what you want, and then you can get this sort of, look like a transparent film because they're only 50 nanometers in size, and then you can check to see if it actually does the optical transport that you expect. Okay? So we're basically working on creating a foundry, okay, that has all of these elements in them so people can do process development and prototyping. So we're really aimed on 2 process lines. One's a roll-to-roll unit operation where we have all of these pieces. Some of them that we're developing in-house, like nanoscale encapsulation. So we're doing slot type coating, which is very old, but what we're doing is we're making the films only 10 nanometers thick, which, best of my knowledge, has never really been done before. We're doing a roll-to-roll transfer of graphene, where we peel off essentially one layer of graphene and put it onto a flexible polymer substrate. So you can use this maybe for a touch screen or some kind of a conductive transparent film. Do nanomaterials deposition for printed electronics. High-speed metrology like scatterometry. Imprint, which I'll talk about in detail. Metal and dielectric depth. Plasma and wet etch, and of course the multi-scale modeling. So the green ones we're developing at nascent, the red ones we're working with partners to develop tools for this. And ultimately we want to be able to demonstrate that these all together work. Now, we're not going to make a smartwatch, right? But we'll make, say, the polarizer for the smartwatch and demonstrate that it works. Okay, that's our goal. So we'll make components of an exemplar device. So we have a roll-to-roll unit that we're making, and then we also have a wafer scale unit, which has a lot of the typical wafer scale processes you'd imagine. But we also do things where we can do this, where we shade with crystalline silicon or other crystalline materials that make them flexible. Do again the nano imprint, and again develop modeling in multi-scale simulation. So here we're working on things like making low power terabit magnetic memory. Both by bit pattern media, but also using other techniques as well. Okay, so that's sort of the big picture of what we're trying to do in the center. And so if you think about patterning, so now I'm going to kind of drill in on what kind of unit operations there could be. So we can't go after all the unit operations in the center because we don't have people or money. So I'm going to just sort of drill down on a couple that we're working on. So in terms of patterning, right? So this is oftentimes one of the key steps when you're making a nanostructured device on the surface, right? Basically, usually lithography, etching, and deposition, okay, in various combinations. And so the first one is the lithography step where you pattern. So there's lots of ways of doing it. There's the classic workhorse of optical lithography. There's thermal imprint, UV imprint, there's electrochemical machining, contact transfer printing, direct writing with pens and inkjets, and directed self-assembly. And so the idea here is you want to have scalable processes, okay, that are robust and flexible enough that you can use them to manufacture lots of devices, not just wire grid polarizers, not just big pattern media. You want it to be more general so you can use it to make all sorts of different things. So I'm going to focus the remainder of the talk on 2, basically UV imprint and directed self-assembly of particles. Okay? So, Okay, so let me give you a little background on UV imprint lithography and then I'll tell you about what the modeling challenges are here. Okay, so UV nano imprint lithography was really invented by my colleague Grant Wilson and I think successfully commercialized by Molecular Imprints, which was started by Grant and one of my colleagues in mechanical engineering, S.V. Srinivasan. And so the idea is the following, is that you have your substrate. You can imagine it's a silicon wafer, okay? And then what you do is you make a template out of quartz, right? So it's transparent. And this template has features that are, tens of nanometers in scale or size, right? And this template is basically made through a painstaking EB lithography process, okay? The templates can be, roughly a square inch in size. Some of them can be, as big as, 3 or 4 inches across. They take a long time to make, and they can be very expensive. For some of the bigger templates, they can be $500,000 to make. Now, when you make that template, that's actually a master. You then use that to make submasters, and they're the ones that you would actually use for the printing. Okay? So what you do is you basically inkjet a photocurable monomer. Okay? You squish the template down onto the fluid, and then through a combination of viscous and capillary forces, which I'll talk about in detail in a minute, you basically fill the template. You shine light through the quartz, you photocure it, and then by basically pulling on one side first, you peel off the template, and you get the structure, and then you can basically repeat it, and it can just keep going. Okay? And basically create your pattern. This has basically been shown that you can make structures 20 nanometers across quite easily. I think the record is John Rogers imprinted with carbon nanotube, which was like 2.5 nanometers, and basically is able to read the shape. You can imagine also doing this in a roll-for-roll fashion, where you just continuously inkjet the droplets. You have a roller that has the desired pattern. You squish it down, and then you have your UV light here. There's some interesting reaction engineering issues related to this because there's a time required for the photo curing, and that determines the speed at which this can occur. And so having this flat structure actually limits how fast you can print. So sometimes what you might want to do is actually have this wrapped roller where you can shine light over a larger distance, so you essentially have a greater reaction time. Another implementation, which is the one we use at Mason in our prototype machine, is more of a semi-batch version, where you have the flexible substrate, you spray the droplets, you advance it, then you have a template that you push down, do the whole imprinting step, lift up, advance it, and then repeat. Right? So it's not continuous, but semi-batch. That's okay. We're not trying to print paper towels here, right? We don't have to do hundreds of meters, a second, okay, or a minute. All right. What we find is that you talk to companies like Applied Materials or Tokyo Electron or Lam. What they would like is for you to be able to do something on the order of 1 to 5 meters a minute. Okay, and we're in that range in terms of printing speeds.
Is environmental vibrations a problem in mechanical?
Okay, so that's a great question. So the thing is, because we're printing, we're basically moving the rollers relatively slowly. It's not. There really is no significant vibration for our system. Now, one of the challenges of printing on flexible substrate is overlay, right? Because oftentimes you want to do things in layers, right? And so now you have this challenge of, okay, you printed it once, now when you come back and do it, how do you make sure you're in exactly the right spot? And that's tricky in a flexible roll because you're pulling it, so there's tension, and so it's being pulled in one direction. It may not be quite uniform, so you can easily be off tens of nanometers in one direction or another, which for making like a very high-end logic device would be unacceptable. Okay, so there's certain things that you can't, certain length scales you can't print by overlay. We have a trick to do 2 layers simultaneously, where you have perfect overlay by having multi-layer templates. It's actually through something called a SAIL process that HP developed. But in general, it's not the same as like multiple processes for newspaper printing or magazine printing. It's much, much slower. And so we don't have to worry about the vibration issues and a lot of instabilities like that. So, so why is everybody excited about UV nano-imprint lithography? So a big part of it is lower cost of ownership, right? So this came out of a recent SPIE paper where they were looking at how much does it cost, to basically produce a wafer. And so this is sort of the standard optical lithography with immersion lithography. We'll call that cost 1. The EUV is greater than 1, and this EUV is slightly less. Personally, I think this is quite hopeful because no one's really demonstrated that EUV on a large scale is really going to work. Like my colleague Grant Wilson is actually willing to bet large sums of money it never will work. So, but the whole point of this paper is that they were like, okay, let's assume that all those very positive, optimistic estimates from IMEC and Intel are correct. Imprint lithography shows a much lower cost of ownership, so it's a lot cheaper to print using this technique. Okay. The other advantage is it has very low material waste. All these other ones you have to spin coat these expensive resists, and so you throw, as you see here, right, you throw away a lot of the product and you don't get to use it again. But in the UV nano imprint, you spray only the fluid that you need. You basically drop exactly what you're going to use on the system. Okay. And then, as I mentioned, you can do extremely small features, right? So this is actually that paper from John Ryder's group where they created a master using a carbon nanotube. Okay, so here it is here. And then they were able to essentially replicate that structure. So it's about 2 nanometers, 2.5 nanometers in size. So basically, UV nano imprint seems to be a path to very, very small features. Okay, so where is this being used? It's already used on prototype instruments for bit pattern magnetic media. The company is now called Canon Nanotechnologies that bought molecular imprints last year. And so they've actually built prototype tools that have been used by Toshiba and others for making it. It's also being used to produce prototype wire repolarizers. And then the future is to do NAND flash memory and DRAM structures. Okay? And so in order to achieve these goals, however, certain process milestones have to be met. Okay? So first is the template manufacturing. Okay? It's expensive and it's slow. Okay? As I mentioned, you have to do this as E-beam. Costs quite a bit of money. So how do you do it? So the way that this problem is being addressed is really through work in Paul Neely's group, University of Chicago, and Grant Wilson's group at UT, where they use block copolymers, which they basically have 2 polymers with 2 different materials. You basically engineer the surface so you can get them to line up. So this is the A polymer, B polymer, etc. Okay. And then what you do is you can etch away one of those polymers selectively, and you can get these nice straight lines. So now you've created your pattern, you can etch it in this material, and then use that to make your template. Okay? So that's the idea there. It turns out that one of the key challenges for imprint lithography is purely a throughput issue. Okay? And it turns out that the rate limiting step is the fluid mechanics. It's how long does it take you to fill those features and fill underneath the template. It turns out the photochemistry is very fast. It's a couple orders of magnitude faster, and the inkjetting is very fast. And so what they need to be able to do just to hit NAND flash memory is basically something around 1.5 seconds, which they're just able to do now. And I'll tell you how they managed to do that through helpful modeling and simulation. In order to get to the rates required for logic devices, it has to be significantly smaller. The other issue is defect density. Okay, it's too high for both NAND and logic devices. Right now, they're somewhere around 5 to 10 defects per square centimeter. So these are like unfilled regions. Okay, they need to be basically a couple orders of magnitude smaller. Okay, in order to do that. And so here, this is a lot to do with making sure the fluid went everywhere you wanted it to go. So what I'm going to do is talk about how does modeling and simulation help you figure out how to make that happen. Okay? So this fluid management in the UV nano imprint is really the key process, right? So you want to fill this in less than a second. So the questions you can ask is, well, how many drops should I spray? I mean, why am I spraying multiple drops anyway? Why don't I just put one big drop? Right? Well, I'll explain that to you and convince you why it should be many drops. Okay? Then you can ask the question, where should I put my drops? Is there an optimal way to arrange my droplets? And what's the best you can hope for in terms of the waiting time before basically make sure all the fluid went where it wanted? Okay? And then how about minimizing the defect density? Okay? How do I get to this number? And really the primary cause of defects is trapped gas. Okay? You're pushing down these droplets and you trap local regions of gas. Okay? So here's an example of a little gas pocket that gets trapped. Now what's amazing is that this gas actually goes away. It dissolves if you wait long enough. Okay? And of course what you want to do is you don't want to wait very long. So how do I make sure that this gas diffusion step is as short as possible in order to basically get the shortest waiting time, which results in a low defect density? Okay? And so it turns out simulation provides a nice tool to answer these questions. All right, so let's talk about fluid mechanics. So what we did is basically develop a simulator, a multi-drop simulator for what to describe what's going on here. So you can think of this as the substrate, here's the template. I'll start off with just a perfectly flat template, and then I'll generalize it to a pattern template in a minute. So you have a fluid, this is one of the droplets, and as soon as you bring the template into contact, these surfaces have been designed to be wetting. Okay? The bottom surface is very wetting, the top surface is not so much wetting. It's still wetting, but not so much, because you want to be able to peel that top template off after you cure. Okay? So this is the contact angles, this is the height, this moves with some velocity v. If you look at this, right, there's a curved surfaces here, so the capillary pressure inside the drop is negative relative to atmospheric. So that means that there's a capillary force that wants to suck the template down onto the wafer. Okay? Now, these droplets, when you first put them down, are like 100 microns across, and when the template first touches, it's like 1 micron high. So the aspect ratios are quite different. Okay? And at the end, you want to have a film that's 10 nanometers thick. And again, it's over a square inch. So basically, your horizontal length scale is much larger than your vertical length scale, so we can use everybody's favorite equation, the lubrication equation, to describe what's going on. Okay? So we solve the lubrication equation, which tells you the relationship between the height, the pressure in the liquid, the viscosity, and the velocity of the upper plate. You can figure out the velocity field, and you can solve this equation. You can figure out the velocity field, advance your interface, okay? And then, of course, at the interface, you have to apply this capillary condition in terms of what the pressure is, okay? So let me just point out one key parameter. It's this gamma hat. So it's essentially the surface tension weighted appropriately by the two contact angles, okay? And so we do this with a volume of fluid method. I'll show you simulations that can do up to 1,000 droplets. In practice, when they do this on, say, a square inch, they're spraying about 10,000 to 20,000 droplets. I can't quite do that many droplets yet. I bet I'll be able to do it in 18 months, okay, in terms of improving our parallelization of the code. Though, in fact, in practice, we may not even have to simulate more than 1,000 drops for this to be a useful design tool, as I'll talk about in a minute.
Just a quick question. In any of your simulation, do you have to make any corrections for the nanoscale effects for boundary conditions?
Great question. We're not. In short, we're not. We assume continuum mechanics is fine. I'll tell you my justification for that is that when, everything I've ever read in the literature, as long as you're more than about 10 mean free paths of the molecule, continuum mechanics works, and we're way over 10 mean free paths. Also, I'll tell you that when they do the alignment on their actual tool, they actually can measure the force required to slide the template over the wafer. And when you look at their results, and I just use a very vanilla continuum mechanics model, I can match their data perfectly. So there basically doesn't appear to be any slip or anything like that.
So for all fluids, whether it is liquid phase versus gas phase, or there is then some accommodation or none of that.
Yeah, it all seems to work. Okay, so here's just a simulation for 1024 drops. just to show you what's going on. So here's the height. And so in this simulation, I'm assuming that the template is force-free, that fluid is basic, that the template moves down just by the capillary forces. And that sets the velocity. So the droplets get bigger and bigger and bigger as they spread, and eventually come into contact. And here, so one thing I'm going to point out, right, is that I neglected the gas, right? I will justify why neglecting the gas is usually okay. Not always, but usually okay, right? Again, of course, what happens is the pressure increases underneath the template. It turns out that if you have, very few drops, the pressure can actually increase so much that you can deflect the upper template in a way that's too much for good accuracy in reproducing the template image. If you have lots of droplets, it doesn't matter so much.
Does that mimic like the actual droplet geometry? I mean, I'm looking at it, these like seem like perfect circles that you're starting with, and there's perfect row.
Yeah.
And I would
It's pretty much like that. I mean,
this is the real image.
This is a real top-down image after it's moved some distance down. They didn't put theirs in a perfect square lattice. It's a little bit off, but they really moved like perfect circles. Okay. And then I'll show you in a minute why you sometimes get this one. This one turns out it's for a pattern template where the flow is favored along one direction versus the other. Okay. All right. So here I'm going to so here's big takeaway message number one. Multiple drops decrease the fill time. Okay. So here I show a simulation of the height, say normalized from where you start to say an ending point. That would correspond to say 10 nanometers, right? So the height basically drops down. Okay. It turns out it drops down like t to the minus half. And what you see is if you go from 1 to 25 all the way to 10, 24 droplets, it gets a lot faster. Okay? And so and essentially you can actually do a little model and scaling analysis. And what you find is that the filling time is inversely proportional to the number of drops. So you get, essentially, if you have a lot of droplets, you can really reduce the filling time. Okay? And so, so we actually figured this out about a decade ago, actually. And this is essentially how they do all their, and this is really what motivated them to do all their filling using spraying down multiple droplets. Okay, you can take all this data and basically put it onto a single master curve, which we basically derive. Now, of course, what happens is that at this point here, right, if I zoom in over here, this corresponds to the point where the droplets touch. Okay, so at that point I deviate from my theory, which assumes the droplets don't interact. But what's amazing is that all of these still collapse onto a single master curve. And the scaling is a factor of 2 off, but that just means I take this t-fill and put a 2 in front of it, and I get the right answer. Okay. All right, so that's message number 1. Okay, you don't have to do this with just letting capillary forces work. You can also push down the template to speed things up if you wanted. And so that's what these simulations show. Again, so here's the height as a function of time. So 0 newtons means I'm just letting capillary forces do all the work. That's this red. The red is the analytic. The black is the simulation. I could squeeze it with a force, and it does go faster. Not a lot faster, but it goes faster. Okay. You might also notice that the slope here is different. It turns out that if you apply the same theory, you find out that it goes like t to the minus quarter instead of t to the minus half. But again, the imprint time is inversely proportional to the number of droplets. So put down a lot of droplets on the surface. This blue curve here is, what if you put the drops in a not square array? Okay, this was actually slightly randomized. And you actually get a really, now you're talking an order of magnitude difference in terms of the imprint time. So there is this optimality. It turns out that if you have a flat template, it's a square array. It's the best way to go. Okay. All right. Well, but real templates have a pattern, right? Yes?
How do you deposit the droplets?
They're inkjetted.
Okay, that's easy.
I wouldn't say it's easy. I mean, I'm going to say it's easy because I'm a theoretician. I know that what the company does is they buy them from a company in inkjet heads from this company in Cambridge. I forgot its name. And at this point, it's essentially plug and play. Okay, so everything I talked about was with a flat template, but real templates have patterns, right? And so one of the classic patterns is the line space pattern, okay? So here I show a line space pattern where you could have a separation, D1 and D2. I'm going to assume in all the calculations I'm going to show that D1 and D2 are equal to each other. You have the height sort of above the teeth of the cone, if you want to think of it that way, and the depth of the feature. And so what we do is we go back to the lubrication equations, and we basically replace this by anisotropic permeability. Okay? So flow is going to be different whether you go along the teeth or across the teeth. Okay? So what we did here, in the results I'll show you, is that we took I basically developed an analytic model for this permeability. Okay? In principle, you could do the full-blown simulation through this complicated structure and just tabulate the permeability and use it later. Okay? I just happen to do it this way here to figure out what goes on and basically do the simulation. Okay? And so what happens there when you do the fluid spreading is initially it spreads like a circle. There's not much happens. But then what you start to see, it starts to favor flow along the lines. Okay? And I should make one comment back here. I only draw like one line here, right? But keep in mind, these features can be like 20, 50 nanometers wide. This droplet, in practice, is like 100 nanometers wide. So this is just meant to give you the feel of which direction the lines are going. The actual line space pattern is actually much, much denser, right? So what happens is that you favor basically flow along the lines. Okay? So this happens essentially because the permeability along the lines, especially as you get the template gets very close to the surface, is higher than it is across the lines. Okay? As you go across the lines, you're getting to the point where you're basically preventing flow. But even if the template touches, there'll always be a path through the teeth, if you like, this way. So you basically get these filled structures here, and what you're waiting to do is fill the fluid in these unfilled channels here. Okay? There's also a capillary effect that goes on as well that helps promote the flow in this direction as opposed to the crosswise direction. And this is actually seen. We actually found a patent where they actually observed this phenomenon here, where the lines were going this way, and clearly are seeing the favored flow along that direction. Okay. So what does that mean in terms of the filling? Again, it's always better to have more droplets. And so here I just sort of show what happens. I also show what happens the higher these teeth are. Okay, so you basically have a bigger effect the higher the teeth. And when you notice what happens is that when you have very large teeth, it rapidly drops and then seems to start come again before it fills. That's because you first fill rapidly in this direction, and then you fill across. And so that's why it comes across as like a two-step process. Okay? All right, so now, what does this tell you about where you should put the drops? Okay? So you can put the drop placement for different features, right? You could have lines, and say maybe it's flat over here. The lines could point this way, or you could just have two different sections. So how do you put the droplets? So there's basically two, I'll tell you two schemes we can employ. So one is, we just put the same droplet volume everywhere, okay? Or we put the droplets with volumes proportional to the features that they have to fill. So essentially, if you have to fill more fluid in that region, put more droplets or make the droplets bigger. Okay? And so what we find is that makes a big difference. Okay? So here's the height as a function of time. So all these bend curves with a big knee is if I didn't distribute the fluid very, very thoughtfully. I just made everything equal volume. And the faster ones is if I put the fluid in proportion to where it's needed. Okay? So here's what happens if you don't put it that way. Yeah, I've got plenty of fluid over here, but too much. Now I've got to move that fluid over this distance with a gap that's really thin over a large area. It takes a long time for the fluid to move across. Okay? So what you want to do is you don't want to have excess fluid in one side and a fluid deficit in the other. So the second big rule, okay, the heuristic droplet dispensing scheme is where do I put my fluid in proportion to what I need it to be. Okay? Lots of drops in proportion to what I need it to be. Okay? So they actually do this at molecular imprint. So this is actually a schematic of what they've done for making doing the patterning on a wafer. Okay, so they actually slightly bend the wafer before they bring it down the droplets. It helps with the gas transfer. They put down, they print. And so here I show basically droplets, and they've distributed them in proportion to what the feature density is, right? So they put lots of droplets where the features are the densest. They put fewer droplets where it's not dense. They bring the template down. And so just looking at a movie, what happens. So right, as the template's bend, it spreads out, and you basically don't see any gas trapping. Okay? And it does it, relatively quickly. Okay, so now, this should all beg the question about what happened to the gas. Okay? It's not all being swept away just by curving the interface. They're trapped in gas bubbles. And what's amazing is that most of the gas bubbles go away. Okay? So here's a picture of, right at the inception, right? And they do. You can even see, just like we see the nice little sharp diamonds, they get these unfilled pockets as well. Okay? So you can do a little model to figure out, how big are these pockets as a function of time. What happens is you have more droplets. And essentially, it turns out that you're, again, better off having lots of droplets because when you have lots of droplets, the size of these defects essentially scale with the number of droplets. So if your goal is to have as small defects as possible, okay, then lots of droplets help. Okay? And one thing that they oftentimes quote is that, if you double the number of droplets, you can basically decrease your waiting time by a factor of a few orders of magnitude, actually. You can see how sensitive that could be over here, right? Going from 100 droplets to 225 droplets can really decrease the size of the defect. So, we came up with a model to simulate the gas dissolution of these trapped pockets. It's basically a simple mass transfer model of these trapped pockets, which we just model as cylinders. We go off and solve it. But I want to just point out the key parameter in this model is the diffusivity of the gas and its basically partitioning function in the photoresist. Okay? And so here I show, again, sort of like what the defects would be as a function of time, okay, for 3 different values of alpha, which go from 10 to the minus 4 to 10 to the minus 6. And these numbers are the range if you can use helium, argon, or nitrogen. Okay? So helium basically gives you the highest alpha, so it's got the highest diffusivity and the best partitioning in the resist. Okay? Nitrogen has the worst, and it gives an alpha that's a couple orders of magnitude slower. So what happens is that you basically have the imprint step going on, okay? And then you get these features that are trapped at this size, okay? The pressure builds up, and then they dissolve. And this gives you a sense of what the time scale is for that. So for these smaller, bigger values of alpha, it can be anywhere from 1 to 10 seconds of waiting time to get rid of them. But if you're down around helium, then you can do it much faster. And in fact, in many of their tools, they actually go below helium over the system to basically use that as the gas, so it makes it easier to dissolve. Okay? So again, remember, imprint time is all about how long you want to wait. And so essentially, if you have this the highest value of alpha, the amount of time for diffusion and filling are about the same. If you use these other gases, you're going to be spending most of your time waiting for the gas to dissolve. So let me just say one last thing, and that's really about these template features. So you might say, okay, when I put these templates down and I have a drop here, okay, where does the fluid go? Or where does this gas go? Well, it turns out, again, it just dissolved. And essentially did a little model similar to the one I just showed you. And again, what you find is that at first these features get filled via capillary forces, that's the first branch, and then just dissolve. Okay, that's the second branch. Okay? And what you find is that for very small features, you can fill in less than a second. Okay, so this is actually why this technique seems to work so well. It's because the gas just, the size scales are right, the gas dissolves efficiently. Okay. So this is just an image of one of the tools. So this is one for the bit pattern media. This just shows you a robot picking up the disk, sticking it in there. Okay, you can't see it, but they spray on the resist, and now they're pushing it down. They fill it. You're going to see a flash of light. So of course you can't see the patterns because they're nanometer scale, and the robot picks it up, and you can go off and do the next one. Okay, so the value of these UV imprint simulations really tells you two useful things, right? One is that lots of drops decrease the build time of defects, right? So it allows faster flow, and it really allows smaller, faster dissolving defects, okay? So here's actually some experiments showing that also if I have smaller droplets, but of course my total volume is the same, my spread time decreases significantly, and also make sure that my defect density is lower. And the second one is put the drops where they are needed for filling, right? So that's like the first order heuristic drop placement algorithm that you would use, okay? Now, where detailed flow analysis needs to continue and where we're working toward now is that if you want to make a more complicated structure, right, this is probably not showing up very well, but this would be like for a logic device. This is actually a lot more complicated than lines and spaces, right? It has mesa areas, it has these complicated structures, and so you really need to, now it becomes a little bit trickier in saying, well, where should I put my droplets? How should I place them? What's the pattern? And so here it really comes down to figuring out how do I take my permeability. I have to basically go back to that permeability model and essentially divide up the space and identify local regions of permeability, and then maybe simulate what goes on, not necessarily over the entire square inch of the input pattern with the 20,000 droplets, but maybe just at border regions where lines and spaces reach mesas, or lines and spaces reach dots, or something like that. And that's why I said earlier that we may not even have to simulate 20,000 droplets. Maybe 1,000 droplets are fine as long as you focus in on the region of interest. Okay, so looking at the time, it's only about 7 minutes. So I guess I'm going to probably skip this section because I thought there were 20 minutes and I don't want to keep people over. Okay?
Like to catch too.
Yeah, I'm not so worried about the plan, but I'd be happy to talk to answer questions about this if you want. But let me just, sorry about not timing this very well. But let me just kind of close with the benefits of this unit operations approach. It really gives you a scale-up methodology. If you take these things that are a large area, high speed, and low defectivity, if you have models, it gives you a better tool or a broader tool for process exploration and innovation, and also figuring out how to mix and match processes to make things work. Of course, models find the right provide a framework for process control, or mechanical engineering, call it real-time decision making. And ultimately, the goal here is to accelerate time to market. Okay, what everybody's really pressed for now is that we don't want to discover a new material or a new structure and then take 20 years to get this to market. We want to be able to do it in 5 years. Okay, and so really, having well-established manufacturing tool set, well-established models would help people accelerate more quickly. And I think chemical engineers have a lot to contribute to this area. So I'll just acknowledge my collaborators and my funding sources and open it to questions.
Hi, how do you confirm that you have 20 nanometer stripes, things like that?
The way it's done in practice is that basically print it out and then cleave it and then just do an SEM.
Okay.
In your model, do you have like a uniform distribution of gas dissolved in the droplet? And then I didn't see a mass transfer coefficient at the, you said a partition coefficient. So I understand that drives the equilibrium at the interface, but you'd have diffusion within the droplet, and then you'd have a resistance at the interface, which would be the mass transfer resistance, right?
Yeah, I'm assuming zero mass transfer resistance in the gas, and I'm assuming all the resistance is in the liquid phase, and I had a diffusion coefficient of the gas in the liquid phase.
Okay.
And we have a model to basically essentially estimate the characteristic distance over which diffusion occurs.
So when you're pushing this droplet, is there any other motion out of the plane or away from the plane that could actually help?
Oh, that's a good question. So there doesn't seem to be any motion that would help the filling time, but when they do press this down, what they're simultaneously doing is they're looking at alignment marks to make sure the template is in the right location for the print, and so they actually are making slight sliding motions, really no more than like 10 or 20 nanometers to make sure they're in alignment as the template goes down.
So if we increase the number of droplets per square inch, doesn't the inkjet printing time increase?
It does. I've never heard the folks at Canon say that that's the rate limit, that even then that's the rate limit. So actually, I think one of the other concerns they actually have is that when you spray the droplets down, they're simultaneously evaporating. So you have to account for that while you're, when you inject. Choosing your drop volume that you inject is actually a little bit larger than what you want because you have to account for the fact that evaporation is going on.
And how much of the vapor is actually going into the gas? Because if you're having, if you're sweeping gas with helium, how much of that vapor is actually going into the gas and going back to the
I don't really answer that question.
But my other question is that is there fluid dynamics, fluid mechanics explanation as to why the fill time reduces with more drops?
Yeah, there is. Okay, so the reason it occurs is that the capillary force is essentially just proportional to the area, the radius of the droplet, essentially squared. Okay, it turns out that the viscous resistance force is proportional to the radius of the droplet to the fourth power. And so, by having lots of smaller droplets, you significantly reduce the net viscous loss, viscous resistance in the problem.
Hi, Professor. I'm very mind-blowing to first know about, we try to introduce unit operation into microfabrication because I'm a beginner for photolithography, and one of my professor in microfabrication lectures, he told us, working in a clean room with photolithography is like cooking. So you basically, once you have a working recipe, if you change the equipment in a different national lab, you need to start all again and start to optimize all those parameters. But yeah, if we could introduce unit operation, I think it just do make the optimization process much more easier. But that depends on very dedicated equipment and procedures, and that might be not readily available for all the users currently. And for another, I'm very interested as you talked about that we have different parting density on a master, and we can need to put different density for droplets in different locations so that the liquid would spread better. But I would be more interested in how could we get those air gap out, because for example, if we have an area that's covered with a larger droplets or smaller density of droplets, that area is surrounded by the area covered with more dense droplets. And as those smaller droplets or more dense droplets, while their time to reach full film will be less than those more sparse droplets. So those air gap in the bigger droplets will have no way to come out because they are surrounded by those more dense regions. So how would those air get out, by diffusion or by just dissolving the solution?
So the objective, so what they do now is that they'll say just sort of spray the droplets, then put the droplets down in a square array, meaning they distribute them in proportion to the volume they need filled. They'll do a print, and then they'll look at the result. And and then they'll oftentimes find exactly what you're saying is that, oh, there's a big hole here or whatever, and then they'll just iteratively, by experiment, figure out where there was a big gas pocket, and they'll put a drop there the next time they do the print. Okay? Where it gets complicated is if you have a very complex pattern, it's very hard to know where these gas pockets will occur, and there could be actually quite a few of them. And that's sort of part of the motivation to have a simulation for that. And then the object is you want to then run the simulation with the goal of minimizing the size of those gas pockets so that diffusion works. So one idea that we've patented, we haven't demonstrated it yet, we patented the idea, is that you actually make the template porous to the gas. So now you don't have to just have diffusion into the liquid, you just have diffusion straight up through the quartz. And honestly, I think that's going to solve most of the problems with gas trapping.
Yeah, I have one question. So from what I remember, a lot of these defects, maybe most, come from the release rather than the filling of these pores. And I've heard people talking about either fluorinating the quartz, and I've heard people talking about release layers, the actual film. It seems to me like the release layer would be really important. Has anybody looked into this?
Yeah. So in the original version of the process, they actually made templates that were fluorinated.
Right.
But what they found is that after a few dozen imprints, you've torn off all the fluorinated material.
Sure.
So now what they do is that in the droplets, they actually add a small amount of fluorinated material. What they find is that that there's enough there that it migrates and sort of like replenishes the surface.
So this is mixed within the droplet. It's not a separate.
Correct. It's part of the blend. I mean, so a big part of the product that goes with the imprint tool is the resist. Right. It's more than just a photocurable monomer. There's lots of things in it to get formulated to make it work. And one of them is this fluorinated polymer to ensure that you get as good a release as possible. There's definitely an art to pulling it off, and they have to do things at the edge of the template to induce a crack.
Right.
And pull. They don't. I mean, even though in my cartoon I had it pulling straight up, they don't pull straight up. They actually pull to a certain side, preferentially.
And do you know, with that approach, what percentage of the defects come from the release?
It turns out not so much from the release. Where the release gets tricky is if you make those features more than, say, 3 times the width. Okay? So if you do it then you start tearing off the polymer. And then it becomes an issue of, well, do I need to design it so I photo cure it so that there's more cross-linking and it's stiffer? Okay? Most of the defects are the gas trapping in the environment. And so they spend a lot of time figuring out how to make this, as particle-free as possible. And so, so if you're making a wire beam polarizer, you have a few defects. It doesn't matter. It's okay. And of course, if you're making like NAND flash memory, they're not there yet. But again, okay, if this particular memory cell doesn't work, it's okay. But in logic, you can't have that, right?
We did this at IBM, but we did Whiteside's method of printing a file. But we were doing displays, and the feature sizes were 10 or 20 microns.
Yeah.
So you could get away with a lot of squishiness and defects. Yeah. But yeah, I know.
We're using the flat templates. You use the duplication theory to solve the equation. And when there are patterns, you use the permeability to parameterize the features, right? So the reason is because like when you have loop features, you can apply the duplication theory.
Duplication.
Because you have different scales, right? You have
I'm basically still assuming the flow is unidirectional. So in the model that I showed you, I chose the crudest version where I said I'm going to take the whole thing, the gap in the teeth, and describe it as a single permeability. So we're also working on another version where we have like a 2-layer model where you have the sort of the complete gap, and then you just have the teeth portion, and then just connect the two. And I think that will resolve some issues in terms of accounting for the capillary distance and the capillary pressure difference in the upper layer versus the lower layer.
Okay, so by parameterize the setting by some permeability parameter, you can still apply the place here.
Yeah. I mean, essentially, I'm describing it as a porous medium. And in some sense, that's what lubrication is.
So, how much is the computational effort required for solving this problem of number of points? Like, if I like to just go like hard-headed way that I want to have a film and then a vapor and this insert moving, full-blown nanostones. That's how I want.
Including the vapor? Yeah. Ooh, killer. We tried that. So we've actually, Randy Schunk at Sandia, and he's also at UNM, as a faculty member. We've tried doing that problem. It takes days to do that. It takes days. And the thing is that the gas, honestly, has no influence on the liquid flow. I mean, it's still spread like circles.
Yeah. Once you get into the teeth part, like the assumption that the interface is going to form following that, none of that comes into the picture. You're able to move your interface where you want it to move, right?
So the gas is really, I mean, we've looked at putting in different gas, having a mixed multi-phase, mixed permeability. It costs a lot more time computationally, and it doesn't actually give you a much different answer.
I think we've had a lot of very interesting seminars, but I think this is one of the most important ones I have listened to. Simply because, as you pointed out, I think chemical engineering evolved from empiricism into science. And he's applying all those to an entirely new field of chemical manufacturing. It's a beautiful illustration of what right questions to pose and extract the answers, and very elegant way to analyze application. I really want to thank you for this excellent session.